We're going to continue our discussion of recurrent neural networks. We will pick up exactly where we left off. We're going to be talking about stability, some issues related to why training really deep neural networks is difficult in general, and then we'll introduce the notion of models, long short-term memory neurons, which actually address some of these problems, but come at their own. But all of this, of course, comes with a price, and we'll see if we can actually get to the discussion of what the trade-offs might be. So first, where we stopped off, please your name tags if you don't mind. So where we stopped off in the last class was right here. We were analyzing recurrence. Recurrent neural networks are networks which where the hidden state that is used to analyze any input is passed on for the analysis of the next input. And these are infinite response systems, in that if you have any given single input, the output could continue forever. Right? So when we analyzed it, we tried to analyze it using we went back to our old notion of the streetlight effect. We know what we can analyze. We can analyze linear systems. So let us begin by looking at linear systems and try to extrapolate what we've determined about about recurrent networks in general from what we know of linear systems. So consider this very simple situation. We have a recurrent network as before. This is a one hidden layer recurrent system. So the system has the usual recurrence of hidden values. You have an initial value, and you have inputs at various times, and you have the outputs at each of those times. So let's assume for now that in the hidden layer, all of the activations are linear, right? Now, what is the purpose of the hidden layer? The purpose of the hidden layer is to carry information forward. Now, if you'll remember the very first lecture we had about recurrent networks, the way we introduced the concept, we spoke about, I began by presenting a few examples from Andre Karpathy's page where a recurrent network had generated text, and one of the things it had generated was programs. Now, if they're trying to generate a program, if you open a parenthesis, you must close it. So this means the memory that we have opened a parenthesis must remain with the system until it is closed. Otherwise, what comes out is not going to look like a program. Now, this is a more generic concept. This is, using programs with parentheses as an example is kind of very illustrative in the kind of memory that these systems are required to hold. And the fact that the amount of time for which, the number of steps for which you must hold this memory is quite arbitrary, because what happens between the opening of a parenthesis and the closing of a parenthesis can be arbitrarily long and arbitrarily complex, right? And this is the kind of stuff the system must hold. Now let's see if this little structure can actually do it, and what the limitations might be. So let's begin with the linear system. In the case of the linear system, we're going to assume a very simple activation. All activations are identity functions. So the output y is the same. I mean, the output h is the same as z. Z is going to be w times hk minus 1 times w x hk, which is to say that the hidden activation is the same as the affine input, because the activation function itself is linear. And this value z is just some linear combination of the hidden values of the previous time instant plus some hidden combinations of the current input. Standard, right? So we saw over here, we worked our way backwards, and we saw that what really happens over here is that you can think of the output at any time, k, I'm using k to represent time, as the response of the system to inputs, to the individual inputs at various times. So basically the way we found it, if I were to define my network like so, this is my HF minus 1, and these are my inputs. If you consider the output, let's just speak of the H at any time. This is H1, 2, 3, 4, or H3 over here. H3 was the sum of the response. So if I were to represent H of 3 comma t as the response of the system for an input at time t, then what we found was for a unit input at time t, then then what we found was that we could write H3 was H, how did we have it? Minus 1. In fact, I will just skip this 3 over here. Let's call this HT for now. So this was H of minus 1 times H of minus 1 plus H of 0 times X of 0 plus H of 1 times X of 1, and so on. I'm being a bit sloppy about it with the notation, but the idea that we're trying to convey is that that output is the sum of the response to this term plus 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 the response to this term. It's just a direct summation, and that's because the activation was linear. This is what we found out in the last class, right? Now what this means is if I want to see if a system, if this thing will actually remember things for arbitrary amounts of time, which is what we really want the system to do, as in the case of the parenthesis, right? What we want to see is what happens if I provide some input here. So it is sufficient for me to analyze the response of the input to a single response of the system to a single input at time 0. So ignore HF minus 1. Let's assume this is 0. Let's just consider what happens if we just have a single input at time 0, right? So in that case, here's what we're going to have. The response at any given time t is simply w times h of t minus 1 plus c of xt, right? So from this, we can figure that h of 0 is simply going to be, what was that? W times c of x0, is it? The h of 1, at h of 1 there's no more input, all you have is the h of 0. So that's going to be w times c of x0. H of 2, again there is no more input, you only have the hidden value at the previous time, so that should have been w raised to t minus 1, I guess. This is, can somebody note? So there's a bug on the slide, Ahmed. That should have been w raised to t minus 1. Okay. So this would be w squared x c x of 0, right? So as I keep going down, if all I have is a single input out here, the single input out here, the output at any time is simply going to be w, the hidden value at any time in general is going to be w raised to t minus 1 c times x of 0. So this is all I really need to look at. The entire response is governed by w, right? So what happens for different values of w? Assume that the entire thing is scalar for now, right? So my input is scalar, my system is scalar, we are looking at scalar recursions. So now in that case, w is just a single number. What happens for different values of w? If w equals 0, what would the output at time t be? Just going to be c times x0. It's going to just maintain the same output throughout. What happens if w is less than 1? Wait, if w is 0, w is 1, it's just going to maintain the output. I made a mistake, right? So if w is 1, it's going to maintain its output throughout all time. What happens if w is less than 1? as t goes on, the whole thing sort of falls very quickly to 0, right? What happens if w is greater than 1? It's going to explode, right? And so this is exactly the kind of behavior that you want to have, that you will see. So if it's not really remembering stuff, it's behaving in a fairly erratic manner. For w being slightly less than 1, or if w is less than 1, the input that you provided at time t0 begins falling off. If w is considerably less than 1, it's going to fall to something pretty close to 0 and vanish in no time at all. As it gets closer to 1, it's going to be kept maintained for a longer and longer periods of time. And as t increases, just as w just steps over 1, it explodes, right? So now, is this really the kind of response that we want? Do we want the thing to forget? Now, what does this mean if w is falling off with time? That means it's forgetting, right? What does it mean if it's exploding? The system is unstable. It's not BIBO. It's not bounded input, bounded output. Neither of these are really behaviors that we are really looking for in a system of this kind. So now that was for a scalar input, right? What would happen for vectors? For vectors too, in this case, for the case of vectors, these are going to be vectors, right? C would be a vector, X is going to be a vector, all of these, and W raised to N is going to be a matrix. So for the case, if we're speaking of a network where you're operating on vectors of inputs, the hidden values, you have vectors of hidden values, you have vectors of outputs, then this term is a vector. This is a vector. So this is a matrix. This is a matrix. This is a matrix. This is a matrix. The behavior is governed entirely by w raised to t minus 1 again, but w is now a matrix, right? So if I think of matrices, now remember that W is the matrix that connects the H at any one time to the H at the next time. So what is the structure? What is the shape of W? Is it rectangular or square? Square, because the size of H is the same at every time, right? So if so I can just write H of t as W raised to t minus 1, or I'll just write this as h of t plus 1, so this is a bit more convenient, right? Times c of x0. I'll ignore the c, I'll just call this x0 for now, because we're really interested in what happens with w, right? So I'll just call this x0. Since w is a square matrix, I can write the eigen decomposition of pretty much any matrix, any square matrix, right? So I could write W equals, what would the eigen decomposition of W be? The eigenvectors times lambda times transpose? Inverse, right? It's transpose only if W is symmetric. Right? So what is W raised to N? Or W raised to T? What is this?
U lambda times T or U.
That's going to be U times lambda times T times U inverse. Right? So lambda is going to have this structure, where the individual lambdas may be scalar, or maybe real or occur in complex conjugate pairs, right? So what would happen to lambda t as t tends to infinity, right? What is it dominated by? What happens is if you have a small ratio that's greater than 1 between two lambdas, that ratio keeps getting magnified, because so if I have lambda 2 equals some alpha times lambda 1, implies lambda 2 raised to t equals alpha times t raised to times lambda 1 raised to t, right? So this alpha term, the ratio, or I can just say lambda 2 raised to t over lambda 2 over lambda 1 raised to t equals alpha t. This is the ratio. This is how the ratio of the eigenvalues of w raised to t. These are the eigenvalues of w raised to t, right? So this is how the eigenvalues of w raised to t scale with time. Eventually, w raised to t is going to be dominated by just one single eigenvalue, the largest eigenvalue, right? Now, to see how this influences things, let's look at the Langsdorff's expansion of pretty much any multiplication. So let me say u1, u2, u3, and so on are the eigenvectors within U. They span the space, right? So any vector x, or for any vector h, I can write h equals, I can express h in terms of these eigenvectors, right? So what happens when I multiply h by w? If I multiply h by w, I'm going to get if h is a1 u1 plus a2 u2 and so on, w times h is going to be a1 times wu1 plus a2 times wu2 and so on, right? And what is w times u1? This is the eigen decomposition. So it's just going to be lambda 1 times u1, correct? So this is going to be a1 lambda 1 u1 plus a2 lambda 2 u2 and so on, right? So now if I multiply this again by w, what will I get? If I write w raised to h, so if I say w squared h, that's going to be w times wh, that's going to be a1 lambda 1 wu1 plus a2 lambda 2 wu2 and so on, right? Which is simply going to become a1 lambda 1 squared u1 plus a2 lambda 2 squared u2 and so on, correct? So eventually, when I have w raised to th, that's just going to be a1 lambda 1 raised to t times u1 plus a2 lambda 2 raised to t times u1 and so on. What would happen if any of the eigenvalues were less than 1? That component is simply going to go to 0, right? But then, even amongst the eigenvalues which are not less than 1, eventually, because the eigenvalues are being exponentiated, the largest eigenvalue is completely going to dominate, right? What you're really going to get is, in the limit, t tending to infinity, w raised to t h, is simply going to be lambda max raised to t times the corresponding u times an. Did I lose you?
Yeah, so if it's being exponentiated, why isn't it going to infinity rather than just being the max?
So it's basically as it at any point short of infinity, right?
Right.
The term that's going to dominate is going to be just the largest guy.
Okay.
That is the point, right? We're not really speaking of infinity, we're speaking of tending to infinity. So beyond a point, you don't even have to worry about what the second highest eigenvalue is, right? So this means the behavior of the entire linear system is completely governed by the length of the hidden vector will expand or contract according to the tth power of the largest eigenvalue of the hidden layer weight matrix, right? That's all you really need to worry about to consider now is what is the largest eigenvalue unless, and what is the unless? Unless this term a1 is 0. And a1 will be 0 if h has no components along the largest eigenvector, in which case you have to worry about the second largest eigenvector. And if the H has no components along the second largest eigenvector, then you have to worry about the third largest eigenvector and so on. But if you're speaking of generic behavior, it is sufficient for us to actually worry about the largest eigenvalue. And if lambda max is greater than 1, the response is going to explode. Otherwise, it's going to shrink to 0 very rapidly, right? Either way, this doesn't really satisfy our requirements. It's not holding memory for any extended period of time. It's either forgetting or it's blowing up, right? So what does it actually look like? Let's look at some scalar examples. These are scalar examples. I have, these are vectors. So these are vector linear recursions. I have the standard linear recursion that we saw, and we have these are 4 dimensions. We have a single input where all the 4 components are 1 at time 0. And if you look at the magnitude of the response, here's what you find. That if the magnitude of the largest eigenvalue is 0.9, things sort of fall off, right? Here, the largest eigenvalue, the magnitude of the largest eigenvalue is 1. It just stays stable. Here, the magnitude of the largest eigenvalue is 1.1. It blows up. Now, this is the same diagram. So what is the difference between these two guys? Anybody want to guess? In one case, the eigenvalues are actually complex. So you're going to get this oscillatory behavior, right? In the other case, the eigenvalues are strictly real. The largest eigenvalue is real. So you're going to get smooth behavior. But the general trend overall is going to remain pretty much the same, right? So these are complex eigenvalues. Those are real eigenvalues. So in linear systems, long-term behavior depends entirely on the eigenvalues of the hidden layer weights matrix. If the largest eigenvalue is greater than 1, the system will blow up. If it's less than 1, the response will vanish very quickly. So, and if you have complex eigenvalues, this can cause oscillatory response, which we may or may not want. You can force the matrix to have real eigenvalues if you want smooth behavior, but regardless, the overall behavior is one where everything either goes off to some bad place or everything goes down to some bad place. Neither of which is what we really want. Again, we go back to you kids were not there when we began the lecture. So when we are talking about what we want to hold, we want the system to remember stuff. For example, if you think of the example where the network was supposed to be generating code, if it opens a parenthesis, it must remember that it has opened the parenthesis until it closes it. And the amount of stuff that can happen in between is arbitrarily long, right? And that's not the kind of behavior you're going to see over here. So how about nonlinearities? So this was very easy to analyze. When you have linear systems, linear responses, I can talk about eigenvalues, I can talk about linear recursions. Now, let's try to do the same thing for a system with a nonlinearity. So this is now not just an affine combination. The hidden value is not just an affine combination of the previous hidden values and the input. It's the affine combination passing through some activation. And we're going to see what kinds of responses we get for different activations. So here again, in this case, we are looking at a scalar response. So we just have scalar inputs, scalar hidden values, scalar, and you have scalar responses. Do you mind shutting your laptop? Oh, sorry. Yeah, so scalar responses. And here again, look at what happens to the hidden layer when the first input is +1, right? Look at what happens to the hidden value when the activation function is a sigmoid. Quickly falls to some value and saturates, right? Depending only on the value of W, it saturates at different points. Because now what happens is that although a nonlinearity cannot blow up, a nonlinearity can saturate. It can saturate in the upper direction. It can saturate in the lower direction, right? And so for the case of a sigmoid, this guy simply saturates. In the case of a tanh, it does this, but it does it much more slowly, right? in the case of if I'm using a ReLU, then it blows up in some cases and collapses in some cases. And this is again going to be the same thing, right? The weight must be positive. The input is positive. If the weight is positive, then if the magnitude of the weight is less than 1, it's going to fall off. If the magnitude of the weight is greater than 1, it's going to blow up. Because in the case of a ReLU, if the input is positive and the weight is positive, this is like having a linear activation. Nothing really changes, right? So of these three, if you were going to use one of these for memory, which one would you use? Because it's keeping stuff for a very long period of time, right? It too is saturating, depending on the value of the weight, but it tends to hang on to some information for extended periods of time. So if you've ever wondered why we use tan H's in the hidden activations for recurrent neural networks, here is the answer. Other activations tend to not give you the kind of memory behavior that you would actually want to see, right? Same thing. Here now I'm starting this, instead of starting at +1, I'm starting at -1, the weights are positive. And look at what happens for a sigmoid. Same thing. 2 steps and then it just saturates, right? What happens with the tan H? The same behavior as we saw before. But then observe that if the weight is very small, if the weight is 0, the thing saturates very quickly anyway, even for the case of a tan H. You want the weights to be close to 1. And in the case of a ReLU, why are we getting a 0 throughout? The weights are positive, the input is negative, there's nothing to be had, right? So it just goes to 0. So you get an idea of, I mean, this guy, if your input is negative, this guy has no way of distinguishing between one input and the other, right? So this is for scalars. Let's go back and look at what happens when I have vector networks, meaning I have a vector hidden inputs, I have vector hidden layers, and I have activation functions applied across the hidden layer. Again, same thing. Now in this case, the vector input I'm providing is a sequence of ones, normalized to have a length 1. This is a vector of ones. And you see what happens to I think we're plotting the magnitude of the hidden vector as a function of time. And for sigmoids, boom, it just saturates. You're done. It's not going beyond. After just a few iterations, time instants, it's saturated. For the tan H's, it tends towards saturation, but it kind of remembers things it has some memory-like behavior that you like. In the case of ReLUs, it's peculiar. These weights are randomly initialized, and it tends to just blow up, because eventually you're going to get into this domain where everything is positive and the positive stuff keeps building on itself and the negative stuff zeroes out. So now here I've started from a vector of positive numbers. If I start from a vector of negative numbers, what happens? Same behavior. The sigmoid saturates very quickly. The tan H tends to have some kind of memory behavior, and the ReLU blows up again. So in the case of vector inputs, having ReLUs for your hidden activations is obviously a very bad idea. Having sigmoids is also an equally bad idea, because it kind of beats the point of trying to remember stuff. And tan H seems to be the most appropriate from these figures, right? So, questions? Now, we just sort of showed pictures for the case of the vector responses and the nonlinear functions. If you wanted to be more formal, you'd have to do a more formal stability analysis. And if you want to do a more formal stability analysis, you'd have to consider things like the convergence of Lyapunov functions. Those of you who are electrical engineers here have heard about the Routh-Hurwitz criteria and stability analyses. You'd actually have to analyze the pole zero, analyze Routh's criterion, or pole zero analyses. But regardless of how you do it, you're going to arrive at pretty much the same kind of conclusion, that of the activation functions we've looked at, you want the activation function of the hidden layer must be some kind of a saturating but bipolar function. It can't be strictly positive, it can't be strictly negative. The problem with the sigmoid was that it was strictly positive, that's why it saturates. The problem with the ReLU is that it's strictly positive, that's why it blows up. The tan H is bipolar, so you get better behavior. right? Makes sense, right? You get the intuition over here. And even then, it's going to be sensitive to the eigenvalues of W. And the best case memory is still short. If you go back over here, these things are not going to remember for arbitrary amounts of time. If your program were 50,000 characters long or 10,000 characters long, it's not going to remember to close the parenthesis that it has opened. Right? So how about deeper recursion? In everything that we've considered, we've just considered looking at one time step in the past. What would happen if you looked further into the past, into more time steps? It turns out that if you look further into the past, you just get more interesting modes. So to give you an idea of what happens, let's say I have something that is looking one time step in the past. So if you think of the input as a sequence which has some kind of a periodicity, if the periodicity is 2, so if you get something that, let me draw sinusoids, which does this, and this period is 2 samples, the things are going to add up, and you get positive reinforcement, right? If the periodicity of the sinusoid is 1 sample, then you're going to get these 2 guys adding up, and they're going to cancel out. So as you keep adding more and more taps, you're going to sort of lock into periodicities of different orders, and you will get more complex oscillatory response. But regardless of all of this, if you actually go through all of the analyses, you'd have to go back and again look at all of the Roots criteria and Lyapunov functions and so on. The overall conclusions do not change. These systems are fundamentally unstable. If you have bipolar activation functions, you have some hope of retaining memory for some time. And if you have unipolar activation functions, they're going to blow up or they're going to saturate. Right? Questions? No. Okay. So here's the story so far. Recurrent networks retain information from the infinite past in principle. In practice, they tend to blow up or forget. So if the largest eigenvalue of the recurrent weights is greater than 1, the network responses tends to blow up. If it's less than 1, it tends to die off very quickly. The memory of the network also depends on the activation of the hidden units. So if you have unipolar hidden activations like sigmoids, they just saturate very quickly, ReLUs blow up. So the tan H activations, that amongst the ones that we just saw, are the best ones for storing memory in the long term, but they still have relatively short memory. They're not going to remember stuff for real, not for very long. Right? So just summarizing everything that we've done so far, they're excellent models for time series analysis tasks, prediction, classification, sequence prediction. They can even simplify problems that are difficult for MLPs, but the memory isn't also all that great. And then you have another problem, which is the problem of vanishing gradients, which is not specific to recurrent networks, but happens for all networks, all deep networks, not just recurrent ones. Now, which is how does the gradient of the error with respect to the weights change with the depth of the network? To understand this, consider this multi-layer perceptron. I'm starting with a simple multi-layer perceptron to explain the problem. So in the case of a multi-layer perceptron, consider a very deep multi-layer perceptron. You have some input, you have a bunch of hidden layers, you have a final output. So the output is going to be the final activation. I'm speaking now entirely in some terms of vector activations and vectors because it's convenient to do so. So the output is the final activation applied to the affine combination that goes to the final activation, right? The affine combination is the weights of the final layer times the output of this penultimate layer. So and so on. You can work your way in, and this is just a nested function. The entire network can be thought of as a nested function, right? So if I think of the error that the network makes, the error that the network makes is also a nested function, which is if the divergence is some function of the output of the network, And since the output of the network is a nested function in itself, the divergence too is a nested function. Right? Now, when I write the derivative, this is going back to the simple vector derivation rule. So if I have any function which is f, which is a function which is where f is a function of some w times g of x, then if I try to compute the derivative of f with respect to x, we've seen this chain rule before, which is that this is going to be the derivative of f with respect to z, where z is defined as w times g of x, plus the derivative of w times g of x with respect to g of x, which is simply w, times the derivative of g of x with respect to x. This is just the standard left to right chain rule that we've written several times in the past, right? So, and this guy, this derivative of f with respect to z is simply the Jacobian matrix for the final activation function, right? I'm just using the inverted triangle instead of writing j for consistency. So now, if I have this divergence function, which is a function of the output of the first layer, which is an affine combination of the output of the second layer, which is a function of the output of the next layer, which is, and so on, right? So if I write it in this manner, then if I write the derivative of the divergence with respect to, let's say, any fk, which is in the middle, I can write this using the chain rule as the derivative of d with respect to its inputs times the derivative of f with respect to its inputs times the next weight. We saw this. So this is, I'm just sort of building on this little principle over here, right? So this is, let me write this down. If I have f of w of, this horrible chalk, g of x, then when I write the derivative, this is going to be the derivative of f with respect to its argument times w times the derivative of g with respect to x, right? So we're just sort of using this simple chain rule. And if I use this simple chain rule, this term here is going to be the derivative of d with respect to its arguments times the derivative of f with respect to its arguments times this weight matrix times the derivative of this guy with respect to its arguments times this weight matrix times the derivative of this guy with respect to its arguments, and so on. It's just the chain rule applied. I'm just multiplying all of these derivatives left to right. Yeah. So if I write it down, here is the term. So this is going to be the derivative of d times the derivative of f times this weights matrix times the derivative of f times this weights matrix, and so on, all the way till the point, till the specific variable with respect to which you want to compute the derivative. So each of these, inverted triangle f's are actually Jacobian functions. Remember that they're Jacobian functions. Jacobians are matrices. The w's are also matrices. This is for an NLP, right? And for recurrent networks, keep in mind that for the hidden layers are generally treated as scalar activations rather than vector activations. And as we just saw, if you have a scalar activation, this Jacobian function, as we saw earlier, if you have a scalar activation, the Jacobian can be thought of as a diagonal matrix. Now, we also saw that, so if you go back to this guy, if each of these guys is a diagonal matrix, what is the influence of this diagonal matrix on the entire product? If I can assure you that all of these terms are less than 1, then every time you multiply by one of these diagonal matrices, the length of the product is going to shrink, right? If the diagonal components are greater than 1, the length of the product is going to increase. So now, for most activations, the diagonals or the singular values of this Jacobian are bounded, which means that because your activation functions never have infinite slope, right? Which means that there's a limit on how much multiplying by the Jacobian of an activation function is going to scale up or shrink down your matrix. No limit on how much it can shrink things down, but a limit on how much it can grow it. But exactly what is the limit? The most popular activation function that we just saw was the tan H. So the tan H has this shape. If the tan H has this shape, the derivative of the tan H has this bell shape. The largest value is 1, but pretty much everywhere except at one point, the value is less than 1. So since the value is less than 1, every single one of these diagonal components is at most 1. Generally, it's less than 1. Right? So because, everybody get it? Right. So what happens as a result? When I compute this derivative of this divergence with respect to any fk, every second term over here is guaranteed to shrink the overall vector because it's a matrix whose diagonal components are all less than 1. Right? So this means that as I go from the back and I begin computing my derivatives backwards, unless these w's perform some magic, the Jacobians are going to keep shrinking the derivative, and in a few steps, the derivative is going to disappear and become 0, especially if the network is very deep. Right? So maybe the weights matrices will help us out. Right? Will they? What happens when you multiply any vector by a matrix? So consider this. If I have any vector u and I multiply it by a matrix W, what can you tell me about the length of W times u? Anyone? So, or maybe what can you tell me about the length of W times u as a function of the length of u? What is this going to be? You guys have done linear algebra, right? Everyone here. So what is this number going to be? There are going to be bounds on it.
I haven't done it for a long time. I've seen the left-hand side of this one.
Right, so this is going to be, if I write W equals US V transpose, anybody remember this decomposition? What is that? Singular value decomposition, right? So S is a diagonal matrix. You're pretty much guaranteed that S max, which is the largest eigenvalue, is greater than or equal to this guy, and this is greater than or equal to S min. Right? That was the purpose, one of the purposes of singular value decomposition. It tells you how much the transformation actually influences the vectors. So in that case, what can we say about how these w's are going to affect this derivative? If the singular values of w, but then there's something even more interesting about this. So one way to think about it is, let's say I have some vectors lying on a circle. This is supposed to be a circle, and these vectors are transformed by w. Then the resulting figure is going to be an ellipsoid, right? This would be a largest singular vector, the singular vector corresponding to the largest singular value. This is the singular vector corresponding to the smallest singular value. I'm just drawing it in 2 dimensions. You've got to blow it up in your mind into any number of dimensions. And the corresponding singular, the right singular vectors are also going to be orthogonal to one another on the circle, right? So this guy is going to get expanded to this one. This guy is going to get shrunk to this one, right? So this means that if the input to any multiplication by w lies along one of the directions corresponding to a singular value that's less than 1, it's going to shrink. If it lies along any directions, along singular corresponding to singular values that are greater than 1, it's going to expand. Right? Every singular value has a corresponding singular vector. So if the input to the transformation has components only in this direction, it's going to shrink. If it has components in this direction, it's going to expand. And if the vector is explained by some linear combination of these singular vectors, then the components lying along singular vectors with singular values less than 1 are going to shrink. Those components along singular vectors with singular values greater than 1 are going to expand. So what this multiplication with W at any point will do is that it's going to expand or shrink the derivative that's coming in. And it's going to expand it in some directions and shrink it in the others. So the way you really want to think about it is, instead of thinking about it individually as Jacobians and weights matrices, you can think of the product of each Jacobian and the corresponding weights matrix as a single unit, right? And I can use the same analysis over here. If the single unit has a singular value that's greater than 1, then any derived derivatives in that direction are going to expand, the rest are going to shrink, right? Now here is the strange thing. If you take any random matrix, the number of directions in which the singular values are greater than 1, assuming the whole thing is bounded, is going to be very small. In the majority of directions, the singular values are actually going to be less than 1. So in general, what this means is that as you work your way backwards through the network, some components are going to get expanded, but the majority of the components are simply going to vanish and go down to 0. Right? So what will happen is that as the gradients go down, some components are just going to blow up, because these corresponding to the directions where the singular values are greater than 1. The rest of them are just going to get squished down and disappear altogether. And so the overall behavior you get is going to get something like this. Then this is an example where we've actually had a convolutional neural network, I think MNIST. We have different activations. Well, this should have been TANH, not DAN. But ReLUs, sigmoids, ELUs, TANHs. Each layer is 1024 units wide. Actually, these are MLPs, not even CNNs. Right? You have 19 layers from the input to the output. And the figure shows 1024 units. And this is at initialization. As soon as I initialize the network, what is the length of the gradient computed at each layer? So if it's black, or if it actually gray is almost 0, white is almost 1, they kind of normalized. And you can see that at the output layer, you have several gradients. The gradients all have reasonable values. But then as you begin walking backwards through the network, the gradients become smaller and smaller and smaller, and eventually they all just kind of vanish halfway through the network, right? So these gradients are shown at initialization. What happens as you train the network? If you're performing gradient descent, ideally the gradient is going to keep decreasing, right? Which means that as you go through the training, this figure is actually going to get worse. That by the time you get to the input of the network, the gradients are quite gone, right? So this is with the ELU activation. You can see in batch gradients, you can see that the gradients sort of persist until maybe somewhere here. If I use ReLUs, they become vanishingly small much sooner. If I use sigmoids, they vanish even faster, right? TANHs, even worse. So this is over the entire batch. So you have a batch of inputs, and these gradients are computed over the entire batch. If I consider any single input, then you can see what happens with the individual inputs, and they pretty much have the same kind of behavior. This is with the ELU activations, and you can see that by the time you get to the input layer, the gradients have become very, very small. Right? So the ELU activations seem to maintain the gradients longest, but in all cases, the gradients effectively vanish after about 10 layers. So I'm saying they actually vanish. They all vanish. They don't actually all vanish. What ends up happening is that the majority of them become very small, and you're going to get a very small number of them, so small that you can't actually see them in the visualizations. They become extremely large. Basically, all of the effort is being attributed to a very small number of parameters in the entire network, and the rest of them are being given no responsibility at all by the gradients. So if you actually perform gradient descent, the ones for which the gradients are very small are not really going to get updated very much. The ones for which the gradients are large are going to just assume all the responsibility for the work being done by the network. This is not a very nice kind of behavior. Basically, you will not be able to learn things, right? Because A, the gradients are too small, so those parameters cannot be corrected, and B, the ones for which the gradients are large are going to not be able to do the job because they have too much responsibility being given to them, so to speak. So recurrent networks, again, summarizing, they return information from the infinite past. In practice, they are poor at memorization. The hidden units can blow up or shrink to zero, depending on the eigenvalues of the recurrent weight matrix. And the memory is also a function of the activation function. Tan H's or bipolar activation functions seem to be most effective, but they don't hold it very long. Now, we also saw that deep networks, we were not speaking of recurrent networks, deep networks in general have this problem that as you go back through the network, the gradients tend to behave in bad ways. They tend to vanish or explode. And keep in mind that recurrent networks are really very deep networks. A recurrent network is fundamentally just a multi-layer perceptron where inputs are also being fed at every layer, right? So this is a very deep network. What this means is that if I want to find out how much of the error that happened at this last time is attributable to an input that happened at this time, I have no way of doing it. By the time that gradient is passed back to the input, it's going to either vanish or blow up, right? So recurrent networks have this actually suffer. For standard deep networks, you may stop after 20, 30, or 40 inputs, 40 layers. In the case of a recurrent network, you really have no control over how long the input is going to be. If you're trying to produce programs, for instance, the fact that you opened a parenthesis and never closed it means the network is making a mistake, but for you to realize that this mistake has happened might take 10,000 characters of time, and if you're trying to pass the gradient back 10,000 steps, it's going to vanish. So now stuff gets forgotten for the very same reason in the forward pass too. As things go forward through the network, things get forgotten. Just as whatever happens going backward also happens forward. Just as you're unable to attribute an error that happened way out there to something that happened here, conversely, something that happens here is unlikely to affect something that happens way out there, because as we saw, the hidden activations tend to disappear pretty quickly. Memory is not being held. And that's not good behavior, right? Just as I said in the case of the program, if you're generating programs, if you open a parenthesis, you want to close it. In the case of language, here's another example. Jane had a quick lunch in the bistro, then she. There's this word, she, depends all the way back on Jane out here, and you have no idea what else happens in between. And if this had been Tom, that would have been a he. So you have this very long-term dependence, right? And the length of the dependence cannot be predicted beforehand. So if I have tanh H units, whose memory of this event is going to disappear by here, you have no idea what is going to happen up here. So you don't really want these short-term behaviors. You want something that's more long-term. And that's where we begin going into mystery and magic, right? So we're going to talk about long short-term memory neurons, which form solidly in this domain. Let's go back here. Let's go back and look at our derivatives. What was the problem with our derivatives? The problem with our derivatives was that these guys tended to shrink or expand things. What is the ideal behavior we want? You want them to neither shrink things nor expand things. I want you to hold the knowledge that some error happened over here, and you want it to be passed back until the error is accounted for, right? Similarly, when you're going forward, when an event happens, you don't want it to be forgotten, you don't want it to taper off. You want it to be held until it's compensated for. Like Jane, then you want it to be held till there's a she, at least until there's a she. I mean, this is a simple example. You may actually have to hold it because other pronouns may happen later, right? You open a parenthesis. You want it to be held in this case until it is closed. You want memory to be held, and you want the memory behavior to be dependent not on the parameters of the network, but on the input. Whereas what we found so far was that the memory was dependent on the parameters of the network and not so much on the input. It depended on the eigenvalues of the weights matrix. And that means it's dependent on the parameters of the network. Whereas I want to say, if I see an open parenthesis, I want to remember it. If it's some other gobbledygook, there's nothing to remember. So the memory must depend on the input. Whether something is forgotten must also depend on the input. That's the ideal behavior. So that means you want this term to really just hold the memory. You want it to be a constant, right? Instead of trying to manipulate the architecture of your your parameters and your activation functions, why don't we actually just make it a constant? So this gives rise to something called the constant error carousel. So in the case of a constant error carousel, you have a memory. Your hidden layer is your memory, right? And the memory is just going to go through unchanged unless it's changed by some event. And whether it must be changed or not is computed based on inputs and other data that the network sees, which uses this information to decide whether it must scale down the memory or add to it. So what happens to the memory now becomes dependent as a function of the data that the network sees and its current state, rather than just the parameters of the network which let it forget. So this guy, as it...
Exactly, it's like the current state of the network. Is it not the parameters?
No, the current state is the value of h.
Just the value.
The parameters are the weights, right? And what we saw in these previous cases was the value of h, if I give it some input, h takes some value and then forgets it. And whether it forgets it or not depends on w. You don't want it to forget it based on w. You want it to decide whether to forget or not based on what you have seen. Right? And so that's the behavior that we're going to have with this constant error carousel. It's just going to keep going through straight. And the only thing that it's going to be affected by these gating terms that capture other triggers that decide whether this memory must be retained or whether it must be shrunk or whether it must be expanded. It's a very simple, pretty idea, right? But then once you have this, you can begin building on it. So what are the things that would decide whether the memory must be affected or not? It must depend on what is currently being stored, right? If I've stored the fact that I've opened a parenthesis and I see a closed parenthesis, then I must say, okay, I erase this memory. So whether I'm changing the memory or not depends on the current value being stored and the input. So this gate over here is going to take the current value being stored and the input. But the current value being stored so this is just you could either take it after applying some activation, you can have other stuff going in, there are different combinations, the current value being stored, but all of them are basically doing different versions of the same activity. That this gate term is looking at what the current input is, some function of what is currently being stored, and any other information that it must consider before deciding whether this item tells me that the memory must either be tapered off or must be added to. So, in fact, this guy can be fed to this gate through multiple paths. But you get the basic idea of what is happening over here, right? That the memory is being held, and the memory is only being modified based on what you have seen and what you have inferred, rather than just some arbitrary parameters of the network. This is the key innovation of this particular architecture, which is called a long short-term memory unit, I have no idea why it's called LSTM. Whoever came up with this name had some reason for it that I haven't quite figured out. But the intuition behind it is actually very pretty. Right. So from here I'm borrowing pictures heavily from someone whose name is somewhere on the web. I forget who. Yeah, this one. I borrowed heavily from this particular website for the pictures. So here is your standard recurrent neural network as we just saw it. You have some hidden value. That hidden value and the current input is passed through an activation function to compute the next hidden value. And that hidden value may go out and be used to generate outputs. This was your standard recurrent network. Right? This is drawn slightly differently. We're going to modify this for the long short-term memory. Now it looks kind of weird, wacky, but then let's actually see what this is. This is your constant error carousel. That is deciding whether that is just holding the memory. Now mind you, although I've drawn only one line, this is a vector. So you're going to have a bank of these memory lines going into the page, and that bank can be arbitrarily deep depending on how many different things you think are worth memorizing, right? So that is your constant error carousel. That's the one that's actually, it's called a constant error carousel because the inventors of this architecture thought of it in terms of the error flowing backwards. But this is really a constant information or a constant memory carousel in the sense that the memory is being held unless otherwise modified. So the key component is a remembered cell state. We're calling it a cell. Each unit is a cell. In the past, we just had one simple perceptron. Now it's got a whole combination of things inside it. That's why we're calling it a cell. The key component is this remembered cell state, which cannot be modified by just the parameters of the network, but must be explicitly modified by information from outside. So CT over here is the linear history carried by the constant error carousel. Carries information through, but it's only affected by gates and addition of history, which too is gated. So first, this thing goes through at each time based on the various inputs. You take a decision on whether what is currently being stored must be shrunk. So there's a gate sigma. There are gate sigma with outputs in the range 0, 1, which control how much information is to be let through. So here are the various gates. The first one is the so-called forget gate, which tells the memory it must forget by scaling things down. The forget gate operates on a weighted combination of the previous hidden values and the inputs. So you can see it's some weighted combination of the previous hidden values and the inputs plus a bias. Now observe that I'm distinguishing between the cell state and the hidden state value. The cell state is the memory, but the hidden state value that I'm thinking of is something that has been derived from the memory. Right? The cell state is just an underlying state which holds things. So then the second input has two parts. So this one says, okay, I've done something, I've encountered Jane, and I've said she. Must I still hang on to Jane? Maybe, right? I don't want to get rid of it completely because in this example, something else may happen where I want to pull up pronouns like she. But really, considering that it's been a while, maybe I shouldn't. So you want to be able to taper things down. So you have a way of shrinking the memory. But then you may want to add to it. Think of the case where I've opened a parenthesis. Now if I open a parenthesis, if I close a parenthesis and then I open a second parenthesis, what do I want to do? I want to keep track of two parentheses. I just want to add the numbers. I want to say now I have opened two parentheses, I have to close two parentheses, right? So now in this case, you want to add stuff to the memory. So the way you would do it is you have these two components over here. First, you have this component which operates on the current hidden value and the current input to determine if some pattern has been found, like maybe a closed parenthesis, right? But then you also toss in a gate which decides if this pattern is important or not. So there's a certain degree of gratuitous addition of gates over here. They do help, But this unit together is performing this simple operation of saying, have I found something interesting? Have I found a pattern? And is it interesting enough for me to add to this memory unit? And so the C tilde is a standard tanh activation operating on the weighted combination of previous inputs and the current input, previous hidden values in the current input. This IT is a gate which also operates on the same two things. And what happens over here is that CT now is going to be a forget factor times what was previously stored in it, plus the new memory that's going to be added to it, which is C tilde times the output of the input gate, times this I, which is the input gate, which decides whether C tilde, how much of C tilde is worth remembering. But this is an additive combination to the memory, right? And then you have the output of the cell, which simply compresses the cell state with a tanh. That's it. To make it lie between -1 and +1. We know that tanh is the most useful kind of activation in this kind of situation. So that's what we do. Now, note that what we've done over here is that you want to compress the hidden state. The reason we are distinguishing between C and the hidden state is that we want to be able to carry information. Nevertheless, we know that compressing the hidden state, the nonlinearity is required for a neural network to be able to do useful things. So we separate these two things. You have the hidden state, which is being passed through unmodified, which is C. But then you add this post-processed, the post step of compressing it nonlinearly before you do any other neural network stuff with it. So the A, this guy, this term compresses the C using tanh, and that can in turn be gated with what they call an output gate, meaning you just, in this case again, it's a little bit of over parameterization. You're not just compressing the C and passing it on. You are further deciding whether this must be further scaled based on other factors that you've seen. So while we are adding all of these factors, right, we are adding the hidden state, we are including the input state. Why not also directly let the cell state, the currently remembered cell state, also directly affect the various gates? So what is done in this architecture is that you have these so-called peephole connections, which also let the current cell state to affect the gate values. The peephole connections were added later in the chronological development of this architecture. They were not part of the initial structure because the peephole connections by themselves are maybe a little less intuitive than just using H and T. But it just turns out that adding them improves the performance of the system. So there's a certain degree of, I don't know why in the design of these systems that you just have to live with. So here's the complete LSTM unit. You have this constant error carousel. You have this one gate which decides whether things must be forgotten or not. You have inputs being added where the input itself is computed from a variety of things. And then there's another gate which decides whether that input is worth adding. And then you have the output which comes off the cell state, and the output further affects other things, right? So we have, we've actually sort of gone through the various equations already, so I won't actually go through this guy. Now, when you begin to backpropagate, each unit now becomes a very complex unit, right? If you actually began writing the backpropagation rules, remember that anytime a single variable goes out and influences a bunch of other variables, you have to sort of you have to consider each of these paths when you're computing your derivatives. So it turns out that this is a case where you really want your computer to compute the derivatives for you and don't want to do it yourself. But let's take a look at how I can compute the derivative of the divergence with respect to some CT. So here are all the various paths. This guy, right? And then this guy, and then this guy, and then this guy, right? That's just for CT. And I don't know if there's any other, yeah, 5, sorry, right? So that single cell value goes out into many gates and also goes on to the next cell. And the influences through each of these gates and the next cell all must be factored in when you're trying to compute the derivative of the divergence with respect to the cell value, so it gets a bit painful. Same thing, if I want to take the derivative with respect to, say, the H. here are the various paths that I would have to consider, right? 1, 2, 3, 4, and it goes on. So again, you could write these things down. You'd have to draw that picture slightly differently. It's not difficult. It's tedious. It's not worth your time, so long as you understand what's going on. Yeah, here's more paths that you'd have to consider if you're computing the derivative of h. Right. So I'm leaving this to you as an exercise. If you're feeling masochistic, go back to your office and spend a couple of hours of completely worthless time trying to derive this derivative. Now, the structure actually ends up being a little too complex, more complex than perhaps you need. So there have been other architectures that have been defined subsequently. One of the most popular being the gated recurrent unit. The gated recurrent unit tries to compress a few things. So one of the primary things that happened, if you go out here, is if I go to the previous unit, look at what's happening to this cell state. The cell state is being influenced twice within a single step. First, you have a multiplicative scaling down of the memory. Then you have an additive inclusion of the memory, right? Do we really need to be doing, and both of these decisions are being performed on the same input. So can we not compress them both and say, a single decision decides how much I must be correcting my memory by. I don't have to do this twice. So instead of overcomputing, you reduce the number of computations, and you can expect that the computations will perhaps be more reliable. So here is what happens. Look at what's happening over here. Here now, you have the hidden cell state. In this figure, they're calling it H. But observe that there's no explicit forget gate and then an explicit additive input. Instead, all of that is being performed just once over here. Through this, you're combining the forget and input gates. So if new input is to be remembered, then this means that old memory is to be forgotten. Combine the two, and there's so why compute twice? Then you also, but then if you're storing it, don't actually store explicit hidden values both in compressed and uncompressed format. Remember, we were storing C, but we were also storing tan h of C as H. There were two values being stored. So instead of storing them explicitly, there's some on-the-fly computation and a bunch of other variations. So you will find other architectures of the same kind. There isn't a lot to distinguish between them in terms of the basic fundamental concept. It's more in the details. But the overall idea is something that you should have got by now. Very straightforward. And if you actually look at the literature, the LSTM unit is typically drawn in this somewhat crazy manner, where all of the green dots, I think, are gates, are they? And the blue, the red dot in the center is the constant error carousel cell. Constant error, sometimes it takes me time to decode this figure. You should be able to do it, but the earlier figure over here, these guys are much more explicit and much easier to understand. Right? Okay, you can compare the two, and you'll find both of the same. Now, we were just looking at one cell, but these cells are going to be components in a complete recurrent architecture, right? And as with standard recurrent neural networks, you can have any number of layers of these cells. So for example, you could have multiple layers, except now that each green box over here would be an entire LSTM or GRU unit. And again, remember that each box is now a number of cells going into the page. And anytime I draw a connection from one cell to the other, or even within a cell, they're actually talking across all of the cells, right? So just as we had recurrent neural networks, you can have bidirectional recurrent neural just as we had bidirectional LSTMs, recurrent neural networks, you can have bidirectional LSTMs. The idea is still the same. Nothing changed. The only thing that changes is that each of those boxes now is a LSTM cell, right? So the revised story recurrent networks that were originally designed to remember things are really not very good at memorization. The memory can explode or vanish depending on the weights and activation. They also suffer from the vanishing gradient problem during training, meaning the error at any time cannot affect parameter updates in the too distant past. So LSTMs and their brethren are an alternative formalism where the memory is made more directly dependent on the input rather than the network parameters in the network structure. So this is the key contribution of the LSTM architecture. The memory behavior is no longer dependent on the parameters of the memory structure, but on the input, right? So this is done through a constant error carousel with no weights or activations, but instead direct switching and increment decrement from pattern recognizers. They do not suffer from a vanishing gradient problem, but it turns out that you pay a cost for this, and that when you consider the other parameters, while gradients may not vanish because things go back unfiltered, so to speak, uncompressed, when you begin computing the gradients for the other parameters, they will sometimes blow up. And so now you have to use other heuristics to keep things controlled. For example, people will often do something like gradient clipping, where if the gradient becomes too large, you cap it off and you say you don't let it exceed a specific value. Now, we've looked at the basic structure, the basic problem of recurrent neural networks. What are recurrent neural networks? What are, why they were arrived at, what are their properties, and how do they actually try to hold memory, the dependence on the architecture and parameters, and the extended version of it, which is the LSTM, which holds everything together and is better able to hold memory. But in all of this, I haven't actually come to one very key point. The key point is that when you train these networks, the divergence that we define is between two series, right? Not collections of inputs. And we had a somewhat failed attempt at trying to bring this across in one of our quiz questions. And yeah, he's the guy. I tend to blame my TAs for everything that I do wrong. No, so we have we saw this divergence question, right? Where we define the divergence as something like this. If you had an input and you had a bunch of outputs, desired outputs, at each input you were actually considering a number of possible desired outputs. So consider, for example, the fact that maybe I'm trying to recognize speech. So now I can have various phoneme labels at each instant, and I have some phoneme labels being output at each time. Now it so happens that you cannot really be absolutely certain about these boundaries, right? So if this guy says P2 and I recognize P3 and the network outputs P3 out here, am I wrong? You cannot really be certain because P3 is the next guy out here, right? You want to be able to allow for wiggle even when you're computing error. And how you actually allow for this kind of wiggle ends up becoming quite an issue, right? So, and maybe in the process of training you want to allow more and more or less and less wiggle. So the manner in which you actually compute the divergence becomes not straightforward. For this simple example, for instance, I could, if I were looking at the error, I could say that the overall error is the summation over all time, right? And then for each guy, I am happy so long as it matches one of the three closest ones. So I could say something like the minimum over j going from -1 to 1 of divergence of yt and desired t plus j. So you're allowing it to wiggle a little bit in this trivial little example that I gave you. We saw something a little more complex in the quiz, right? So you can see how simply defining the divergence for time series becomes an issue. And in the next class, we'll actually see how this, how this kind of uncertainty in the definition of the divergence can be dealt with. We'll look at something called the CTC, the expansion of the acronym I will give you in the next class, and how you can train a network under such conditions, and how this also modifies how you actually make inferences from some such networks. Questions?